Hello everyone, welcome back to another video in strength of materials, and in this video we will talk about plane stresses. From my very first videos, we talk about different type of stresses. We have normal stress, shear stress, and bearing stress. And we know that in normal stress is when we have our load P acting perpendicular to the area, while for the shear stress and when we have our load P which is parallel to that area. Okay, now what if we have a structure which experiences both stresses, or there is a combination of normal and shear stress? Now, like for example, if in this figure here, now this is a let's say this is a structure which is being subjected to different type of loadings. We have P1, P2, P3, and P4 that is acting to any directions. Now, if we want to determine the stress at point O at this point, so we need to cut. So let's say if we cut at section AA, we would have our shear stress and normal stress exposed at point O. Okay, so this is the normal and the shear stress experienced by our section which is at point O. Okay, now what if we change our cross section, if we change our cut section, let's say at BB, at point O we would have different stresses, okay, different shear and normal stress, though they are at the same point O. This is because we have a rotation in our stress element. Now, the same as if we have our vertical force, or we have a force that is acting inclined, so we know that at angle theta we have the horizontal component of that force and a vertical component of that force. The same as with this one, if we rotate, let's say this is our AA here, this is our original section. So if we rotate that at a certain angle theta, so our stress, shear, and normal will also change, or will also have their own components, and this is their transformed stresses. So again, due to an angle or due to rotation of our axis, then we would come up with different stresses, different normal and shear stresses, which is relying on the degree of rotation or angle. Okay, now this point O here, this is represented by what we call stress element. Stress element, this is just a square representation of our infinitely small point in our section. Okay? Now, our stress element is this one. This is, let's say, for example, this is the stress element of point O from this figure. Now, at point O, or stress element of point O, there is a normal stress, and this normal stress here is when it is acting away from our surface of our stress element, then that is what we call, or that is a tensile stress. Okay, if it is acting towards the stress element like this one, then that is a compressive normal stress. Okay, and this one here is our shear stress, of course. Now this Y here describes the face of our stress element, so therefore this is the shear stress on the Y face of our stress element. And this X here, this is the direction or the orientation of our shear stress. So since our shear stress is horizontal, therefore it is acting on the X-axis. Again, this is the shear stress on the Y face of our stress element, and it is having an orientation parallel to our X-axis. Okay? Now, on this stress element here, we have, this is normal stress. X here refers to the direction of our normal stress. This is tensile, since it is acting away from our face of our stress element. And this is shear stress. Our X here represents the face of our stress element, and Y as the orientation of our shear stress. So therefore, this is acting on the X face, this one, with a direction parallel to our y-axis. These are the positive phase of our stress element, and this one is the negative phase of our stress element. Okay? Again, this stress element here, this represent the state of stress at a specific point in our structure. Now, if this is our stress element, when we don't have a rotation, okay, let's say this is the original state of stress. Again, when we don't have a rotation. Now, if we want to determine the stress, the normal and the shear stress at section AA, okay, and section AA here, this is angle theta with respect to this axis. So therefore, there's a rotation happening in our stress element. So if we rotate the stress element, and we know that this rotation here is counterclockwise since our angle is acting, or that is counterclockwise, so we would have the stress element here, which is the equivalent state of stress. And then this one here, this is the section AA, okay, or this section here. Now, as what you can see here, this normal stress has been transformed to this one. Okay, there's a transformation of our normal stress, and as well as with our shear stress here, there is a transformation, and it became as this one. So this is the stresses, the normal and the shear stress at our section AA. Now, if we try to cut this point here, if we create a wedge to this, the stresses on wedge, so this is the shear stress at section 4, this is equivalent to the shear stress here, okay? And this normal stress here is equivalent to this normal stress at this point, okay? So it is, they are exposed by just cutting the wedge, you know, at this point here. Or you can just simply rotate our stress element to this one at a certain angle theta. Now, our goal here is to compute for the transform, normal, and shear stress. We have different approach in computing for the transformed stresses. This could be done by using this formula, okay, in which this one here, this is the transform normal stress that is acting horizontally, is equal to the normal stress x plus the normal stress y over 2 plus the normal stress x minus the normal stress y over 2, then cosine 2 theta, plus the shear stress xy sine 2 theta. Now, for the transformed normal stress on the y-axis is equal to the same with the first one. The only difference is that we have the minus here, then minus at this point. Okay. Now, the transformed shear stress, we have this formula here. Okay. Now, for our sign convention, if we have our normal stress that is acting away from the face of our stress element, let's say this one, acting up. So therefore, let's say that's our stress y, that means that is tensile, or that is positive. And if this, and as with this one, if we have stress x and it's acting away from our stress element's face, so therefore this is tensile, so therefore that's positive. Now, for the shear stress, if we have our shear stress on the positive face, so this is the positive face, and the direction of our shear stress here is towards the positive x-axis, so therefore that's positive. Now, if we have our shear stress here that's acting upward or towards the positive y-axis, that is positive shear stress. Now, if we have different directions, so if we have downward or compressive normal stress, negative, okay, as well as this normal stress x, it's still negative. Now, for the shear stress, if we have our shear force acting in this direction or to the negative x-axis on the positive face, again, this is the positive face of our stress element, And if this is the orientation of our shear stress, then therefore this is negative. Okay? Now, if we have at this positive y phase, it's acting downward, that is negative shear stress. So this would be our sign convention for the normal and shear stresses. Now, for the angle theta, if we have a counterclockwise rotation, we have positive angle or positive theta. But if you have a clockwise direction, that is negative theta. That would be the orientation if you use this formula here. But we have different sign convention if we use more circle in solving for our transform stresses. But for this formula, if we want to use this formula, then you have to observe these sign conventions. Now, when we rotate our stress element, there would be a certain angle of rotation that we could come up with the maximum normal and the shear stress. And that is what we call the principal stresses. Okay? And the plane in which we have our principal stresses or the maximum and minimum normal stresses, then that's what we call the principal plane. Now, for the maximum and minimum normal stresses, this is where our shear stress is equal to 0. Take note of that. Okay? So, our maximum and minimum normal stresses occurs when we do not have a shear stress. And that is where our principal plane occurs, or that is the section in which we do not have shear stress. Now, for computing for the maximum and minimum normal stress, we just use this formula here, the same sign convention, but take note we have positive and negative. So if we solve positive first, then negative, then the maximum absolute value, that would be our maximum normal stress. And we have our minimum or lesser negative absolute value rather, then that would be our minimum normal stress. Okay? Now, our principal plane happens at this angle here. So, this is the computation of our angle theta when we have our shear and normal stress. This equation here would be very useful, no, especially when you use more circle instead of this formula. Okay, so later I'll teach you to solve transform stresses using more circle. So this is the max plane shear. Okay, so we have the maximum shear stress. So the maximum shear stress is when we have our formula is square root of, this is the difference of the normal stresses over 2 squared plus the shear stress squared, and this would be the normal stresses acting on the plane of maximum shear. Now let's try to apply the concept of plane stresses in solving problems. Okay, let's try to solve example. I have here at a point on a structural member subjected to plane stress. So we have this member here. Normal and shear stresses exist on horizontal and vertical planes through the point as shown. So this one, we have the normal stress and we also have the shear stress. Use the stress transformation equations to first determine the normal and shear stress on the indicated plane surface, and letter B, the principal stresses. So again, take note, this is the stress element in which we have a normal stress here. This is our normal stress Y, 42 megapascal, and this is our normal stress X, okay? This is 60 MPa, and this is our shear stress, okay? Let's say that's XY. These are equal. So this is 50 MPa. At the same time, this is 50 MPa. So we have to compute the stress on this inclined section. So this inclined section here. So we are asked to compute the normal stress and the shear stress at this point. So if we try to isolate the section here, we would come up with this wedge, in which at this point, let's say we have a compression. This is only an assumption. It's compression, and we have a shear stress at this point. Okay, that's shear stress. Now, however, we do not know yet the orientation of our shear and normal. We can actually be sure on the or in the orientation of our shear and normal when we have computed already the transformed stresses. Okay, so how are we going to compute the stresses at this point? We first compute the angle of rotation. So this is the angle of rotation. Let's say that's theta. So we can actually compute theta since we have the slope or the component which is 8 horizontal, 5 vertical. So that one, in which this our theta, and we know that this horizontal here is 8 and vertical is 5, then we can say the tangent of theta is equal to 8 over 5. This gives us the value of our theta, which is equal to 58 degrees. So therefore, our angle of transformation here is 58 degrees. Now, if we rotate our stress element by a 58 degree rotation, and as we see here, the rotation is 58 degree counterclockwise. Okay? So we have this stress element in which this one is the angle of rotation and this is 58 degrees. Okay? Now, our normal and shear stress here is at this point. Okay? So we have, let's assume that's compression. And this normal stress here, this is the transformation of the stress. Okay? So we know that this is sigma x, correct? So therefore, our transformation here is sigma x prime. Okay, that is the transformation of this normal stress. And there would also be a transformation of the shear stress. So let's assume that it is in this orientation. Let's say that is shear stress x prime y prime. Okay, so these are the transform of this normal and shear stress. Since we have rotated our stress element, so we have our new axis. So this is our new axis here. This is our x-axis. Let's say that's x prime. And this one is our y prime. Or that's our new vertical axis or tilted vertical axis. Again, this axis here were rotated by 58 degree counterclockwise angle. Now, our goal here again is to compute these transformed stresses at this inclined plane. Okay? Again, this is plane here is equal or equivalent to this plane here. They are on the same plane. Now, we have the formula here for our sigma x prime. We have sigma x prime is equal to the sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 cosine of 2 theta plus shear stress xy sine 2 theta. Okay, so let's substitute all the values in our equation. So we have our sigma x prime, which is equal to, now our sigma x here, this is the normal stress along the x-axis. So we have 16 MPa. Now take note, our 16 MPa here is tension or tensile stress, therefore that is positive. So we have positive 16. And the same as with our sigma y, this one, which is also tensile stress, so therefore that is positive as well. So 42 over 2, copy sigma x and sigma y over 2 cosine of 2 times. Now our rotation here is counterclockwise. So if we have counterclockwise rotation, that is positive. If we have clockwise rotation in our stress element, that is negative. Okay, so we have 2 times 58, that's the angle of rotation or the angle of transformation, plus our shear stress xy here. Now, again, to determine the sign of our shear stress, we just look at the positive phase of our stress element. And we know that the positive phase of our stress element are this phase here and this phase. Okay, now the shear stress here at the positive phase is acting towards the negative x-axis, correct? And the shear stress here is acting towards the negative y-axis. So therefore, we have negative shear. So we have plus, now the value of our shear is 50, so we have plus negative 50 sine of our angle here 2 times our theta, which is equal to 58 degrees. Okay, now we have our sigma x prime here, which is equal to negative 10.241 megapascal. Okay, now take note, this is negative, so this is compression. So therefore, we have correct assumption of our sigma x prime here. This is acting towards the phase of our stress element. Okay, now for sigma y prime, this is just the value of our stress here. Okay, let's say that is tension, that's sigma y prime. However, since we only have our stress at the inclined plane, which are our sigma x prime and shear stress x prime y prime, so we will not be computing for our sigma y prime. Okay, so we are only asked to compute for the stresses in the inclined plane. So we have this normal stress, so this is our normal stress. Now for our shear stress, we just have to use this formula here. The shear stress x prime y prime is equal to negative the normal stress x minus normal stress y over 2 sine of 2 times theta plus the shear stress xy cosine of 2 theta. So this is the transformed shear stress. So we have to substitute all the value. That is negative. Now take note, our negative here is the entire fraction. So our sigma x here, which is 16, as we all know, minus sigma y is 42 over 2, correct? Then sine of 2 times 58 plus, now take note again, we have negative shear stress, so negative 50 cosine of 2 times 58. So we have our shear stress here, which is equal to 33.603. This is megapascal. Now this is positive. So therefore, how are we going to draw our shear stress here according to its sign? Now take note, we have positive shear stress. Now we have to locate the positive phase of our stress element. Now we know that we have a new axis for our stress element. So this one is our positive stresses, okay? And now in positive stresses, since we have a positive shear, that means our shear stress here is acting to the positive x-axis and positive y-axis. So we have this direction of our shear stress, this one, okay, that is going to the positive x-axis, and on the positive y-axis, this one here. Okay, so the value is 33.603. So therefore, at this side, or the opposite of this axis here, so we have going downward at this side, and the value is 33.603. Okay, again, they should have the same rotation. If this is one is rotating counterclockwise, so therefore its opposite side shear stress is also, or should be also, rotating counterclockwise. So they should have the same rotation. So therefore, in the opposite side of this shear stress, we have this direction. Okay, we have still 33.603. Okay, so therefore, these are the transformed normal stress and transformed shear stress. These are the stresses on the inclined plane at this point here. Okay? So that's it for our first question. This is question letter A. Now for question letter B, we are asked to compute the principal stresses. When we see principal stresses, these are the maximum normal stresses in our stress element, or that our stress element would experience. Okay? Again, in principal stresses, this is when our shear stress here is equal to 0. Okay, so we'll use this formula. We have two possible equations for this, since we have positive and negative. So we try to use positive first. So we have, let's say, sigma 1 is equal to sigma x plus sigma y over 2 plus square root of sigma x minus sigma y over 2 squared plus shear stress squared xy. Okay, so let's substitute here the value. Our sigma x is 16, our sigma y is 42 over 2 plus square root of, this one is 16 minus 42 over 2 squared plus our shear stress here, this is negative 50, correct? So this one is negative 50 squared. And this gives us our normal stress, which is equal to 80.662. This is MPa, megapascal, correct? Now for the other equation, we have a minus, okay, sigma 2 is equal to sigma x plus sigma y over 2 minus square root of sigma x minus sigma y over 2 squared plus shear stress xy squared. Okay, let's substitute our values here. We have 16 plus 42 over 2 minus square root of 16 minus 42 over 2 squared plus negative 50 squared. So we have our shear stress 2 here, which is equal to negative 22.662 megapascal. Okay, so therefore this is our maximum normal stress, maximum principal stress, and this one is our minimum principal stress. And these are our answer for question letter B. And that's it for our first example. Okay, let's try to solve our second example. We have the stresses shown act at a point on the free surface of a stressed body. Determine the normal stress and the shear stress that act on the indicated plane surface. So we are asked to compute for the stresses on the plane surface. So we have this inclined plane surface here, in which we are asked to compute for the shear and normal stress. Now we have an angle of rotation here, which is 40 degree, and this 40 degree here, so this one is in counterclockwise direction. So if we draw our transformed stress element, we have this stress element here, in which our 40 degree is this one, okay, and this is our inclined plane, which is equivalent to this plane here. Okay, now we have 40 degree, which is rotating counterclockwise, so therefore this would be our new axis. So this one is our new y-axis, or tilted y-axis, and this is our tilted x-axis. Okay, so therefore our normal and shear stress at this inclined plane here is the transformed stress of these stresses. Okay, so therefore we have our stress here, since this is our y-axis. So we have, let's assume the orientation of our stress. Let's assume that it is compression. That is the transform of our y, sigma y. So therefore this is sigma y prime. Okay, And then we also have, let's assume this is the direction of our transformed shear stress. So our goal here is to compute for these stresses. So we are going to use transformed equation. And we also have another method which is Bohr circle, which I will be going to discuss in the next part of this video. So let's try to solve it by using equation or transform equation, which are these equations here. Now, since we are asked for sigma y prime, then we have the second equation. So we have our sigma y prime, which is equal to sigma x, or the normal stress x plus normal stress y, over 2 minus the normal stress x minus normal stress y over 2 cosine of 2 theta minus shear stress xy sine of 2 theta. Okay? So we have our normal stress y, which is equal to, now our sigma x here is the stress acting on the x-axis, which is this one. So we have tension, so therefore this is positive, so 16.5. Now our sigma y here is this normal stress. Now we know this is in compression, so therefore this is negative. So we have negative 38.5 over 2 minus, let's copy sigma x, 16.5. Now we know that this is negative here, and we have negative sigma y, then we have negative minus 38.5. Eventually, this would become positive. Okay? Now, cosine of 2, since our rotation is counterclockwise, so we have positive angle. Okay? Otherwise, we have negative. So, this angle here is 40 degrees, so 2 times 40 minus our shear stress here. Now, looking at the positive phase of our stress element, so this is the positive phase. Now, our shear stress here is acting to the negative x-axis, and our shear stress here is acting to the negative y-axis, so therefore we have negative shear stress. So we have negative, and our, now we have 66 megapascal shear stress, so we have 66, then sine of 2 times 40. Okay, so we have our transformed normal stress in y, which is equal to 49.222. This is megapascal. Take note, we have positive stress, so this is tension. So we have incorrect assumption of our stress. So this should be acting away from the face of our stress element. So it should be this one. Okay? Now let's compute for our shear stress at this point. We have shear stress x prime y prime is equal to negative sigma x minus sigma y over 2 sine of 2 theta plus the shear stress xy cosine of 2 theta. We have here x prime y prime, which is equal to negative. Now our sigma x is 16.5 and our sigma y is negative 38.5, but since again we have past negative here, so that would give us positive 38.5 over 2 sine of 2, we still have positive angle 40 plus, now again we have negative shear stress, we have plus negative 66, then cosine 2 times 40, then we have our shear stress here, the transformed shear stress, which is equal to negative 38.543. This is in megapascal. Now take note, this one is negative, so therefore its direction on the positive face of our stress element is to the negative axis. So therefore we can say that if this is our positive axis in our stress element, so we have our shear stress there, which is going to the negative side. So therefore, this is the direction, okay, to the negative x and to the negative y. So therefore, on the inclined plane, we have here our shear stress, which is going to the right, okay, and the value is 38.543. Okay, and the normal stress is 49.222. So these are our stresses on the inclined surface on our stress element. Okay, that's it for our question number 2. So in the next video, we will try to solve this problem using more circle. Okay guys, so I have posted the link of the part on the next part of this video in the description below. Again, thank you for listening.